Hello, today we're going to be looking at analyzing graphs, which we've looked at before, so we're going to look at polynomials. We're going to make some generalizations. The first generalization we're going to make is about different polynomials and their end behavior. End behavior is the behavior of the graph as x approaches a positive infinity or negative infinity. So some equations that we're familiar with is f of x equals x. We know that that is a linear equation. So if I'm looking at the end behavior here, as x approaches a negative infinity, which means to the left, my arrow's going down. So I have f of x is approaching a negative infinity. As x goes to the right or to a positive infinity, my f of x is going up, which is a positive infinity. Now we're going to switch gears. In our next equation, we have a negative x cubed. Now, if you were to graph this in your calculator, this is the graph that you're going to see. So if we look at this behavior, as x goes to the right, so as I'm going to the right, my arrow's going down, so f of x is approaching a negative infinity. As x goes to the left, which is a negative infinity, my arrow is going up, which is a positive infinity. The one thing that we want to look at here is these are both odd degree polynomials. Even though that's not written, that's really a 1. If we have odd degree polynomials, any odd degree polynomial, the end behaviors are always going to be going in different directions. Now if we switch gears, we have x squared. We know what x squared looks like. We spent a lot of time on our parabolas. So as x goes to the right, so we look right, our arrow is going up. So it approaches a positive infinity. As we look to the left, which is a negative infinity, our f of x or our y is also going up. If I go to a negative x to the fourth, if you graph this in your calculator, it's going to look a little bit weird like this. Negative x to the fourth, as I look to the right, my f of x is going down. My arrow is going down, so my y is approaching a negative infinity. As I go to the left, my f of x is also going down. So when you have an even degree polynomial, they're both going to be going the same direction. It all has to do with that positive or negative leading coefficient. So odd degree polynomials follow one set of patterns, and even degree polynomials follow a different set of directions. And that's what the chart below is all about. So we started off with odd degree. So if I'm looking here, my odd degree polynomials, if the leading coefficient is positive, so if we look here, if my leading coefficient is positive, when I look to the left, my arrow goes down. When I look to the right, it goes right. So negative, negative, positive, positive. So if the degree is odd and the leading coefficient is positive, as I look left, it goes down. As I look right, it goes up. The opposite is true when the leading coefficient is negative. When I go left, I go up, and when I go right, I go down, as you can see right above. Now I think the even degrees are definitely a lot easier than the odd degrees because they're going the same way. If it's an even degree and it's positive, that means it's facing up, so both of my end arrows are going up. If the leading coefficient is negative, that means that it was reflected over the x-axis, which means that it is face opening down and both arrows are going down. You can always just look at your graph to get these answers, but I just wanted to point out these general trends of what happens. Odd degree always goes different directions. Even degrees, it always goes the same direction. are turning points. Now we have talked about mins and maxes, but we're going to be adding in absolute mins and absolute maxes as well. So we're going to add a little bit here. A local min is a point lower than all nearby points. All min values. So if your graph has lots of mins, you're going to include every single minimum value under the local minimum category. Then sometimes there's an absolute min. That means it's the lowest point over the entire domain of the function. So that means that there's no point on that graph that is lower than that point. Local max. Maximum means that we have a point higher than all nearby points. And again, here we're going to include all maximum values. And then sometimes we have an absolute maximum. And this is the highest point over the entire domain of the function. So local min and local max is what we've looked at so far. We're introducing the fact of the absolute. We've had graphs with absolutes, we just haven't talked about them. So something to note is every polynomial has at most n minus 1 turning points, where n is the degree. So what we mean by that, for example, if the degree of my polynomial is 4, it has at most 3 turning points. It doesn't have to have 3, it can't have more than 3. So for example, that would be a 4th degree polynomial with a leading coefficient that was negative. I'd have 1, 2, 3 turning points. It doesn't have to have 3 turning points, but it can't have more than 3 turning points. Okay, so we're going to put all of this together on the next page with analyzing the graph. We're going to look at all these key aspects that we just talked about. So we have our equation x to the 4th plus 2x cubed minus 6x squared minus 12x minus 6. We need that calculator, so we have our y equals, we enter in our equation, x. Now to enter in the 4th degree polynomial, we have this shortcut of x squared, but the caret button underneath the clear that lets us put in any exponent. So x to the 4th plus 2x to the 3rd. You have to arrow to the right or it's going to stay. Minus x squared minus 12x minus 6. We always start off with a standard window. So we go to zoom 6. And I see my polynomial, but I'm missing this bottom part down here. I want to move the graph down. So remember, we hit window. If I want to move my graph down, I'm going to change my y minimum. I'm going to change it to a negative 30. Go back to our graph. And now we can see the entire graph. We're going to sketch that. And remember, it doesn't have to be perfect, but it needs to be accurate. So all of these important points need to fall in the correct quadrant. So like I wouldn't have this minimum value up here in quadrant 2. Everything needs to be in its spot, a sketch of its spot. So we have our graph here. We're going to start with our end behavior. As x approaches a negative infinity, so as I go left, my arrow is going up. So that's a positive infinity. As x goes to a positive infinity, which is to the right, my arrow is going up. So that's a positive infinity. The next calculation we're going to make are the x-intercepts. Those are these points right here. In our calculator, we're going to hit our y equals. Remember, we need to go to y2 and enter in 0. Because when we calculate our x-intercepts, we're finding the intersection point between our blue parabola and our red line. Now we're still having some issues with people using x-intercepts and mins and maxes using the trace function. We never use trace. We use second trace and we make a calculation. So we want our intersection points, first curve enter, second curve enter, and we just hit enter. And it's going to go to one of them. So there's our first intersection point, which is going to be at 2.55, 0. You're going to do that exact same thing again on the left to get negative 2.89, 0. So second trace number 5 intersection. We list both of our x-intercepts here. Now remember, the x-intercept is when the y value is 0. Your y-intercept is when the x value is equal to 0. We can do that on our calculator by going to our table and finding when our x is 0, which happens to be right down here. We can also go to second trace and calculate number 1, the value when x is 0. Or we can use our equation. If x is 0, this is gone, this is gone, this is gone, this is gone. Remember, in standard form, that's the one piece of information that we get from standard form is that y-intercept down there. Our local mins. So in this case, we have 2 minimum values, right here and right here. In our calculators, we're going to do those same calculations. So second trace, we always go to second trace. I can't stress that enough. Where most people that are getting things wrong on the calculator are getting them because they're using trace and not second trace. We want our minimum values this time, so we want number 3. We follow those rules, so it's saying left bound. It's saying go left of your minimum. So if I find the minimum on the left first, if this is my minimum, I want my cursor to be left of that value. I hit enter, then my question changes. Go right, I want to make sure that I cross it. Go back towards the middle, and we have our first minimum value. You're going to repeat that process for your second minimum down here. So we get negative 2.24, comma, negative 6.53, and 1.59, comma, negative 25.82. If for some reason you're not getting the same numbers as I am, check your equation. If you don't know how to use your calculator, please either rewatch some of the videos or meet with me during that independent work time, and I can look at your calculator and we can figure out what's going on. Next, we have our local maximums. So if I look through my picture, here, I only have one local max. We're going to do the same thing, second trace, but this time I want number 4, maximum. It's saying first go left. This is my maximum value. I want my cursor left of it. Then I need to cross that point, right, and then back towards the middle, and we get our maximum. You know that you have your calculation once that word has changed, whether it says intersection, minimum, maximum. So this point is at negative 0.84, comma, negative 0.84. So now that we have all of our calculations, remember all mins, all maxes get listed under the local. Now it's asking us, do we have an absolute min? That means there's no point higher than that point, and we do. This is going to be the absolute minimum value because my graph stops here. There's nothing below it. So I do have an absolute min, and that is that point given there. And it's asking if we have an absolute max. We only had one maximum value, and that was here. This is not my absolute max. Because my graph is continuing above that point, that's just going to be a local max, and there isn't going to be an absolute max. All right, then we have our increasing, decreasing intervals, our favorite part. We always start on the far left, negative infinity. I'm going to my first turning point, and my line is going down, so this is going to be decreasing. So my first interval is decreasing from a negative infinity to that first turning point in terms of x, which is a negative 2.24. And then I change directions, and I'm going uphill. So I'm increasing from a negative 2.24 until this value of a negative 0.84. And then we go back downhill. So that I'm decreasing from negative 0.84 to 1.59. Everything for increasing, decreasing is in terms of x. And then I'm going back up. So I'm increasing 1.59 all the way forever to the right. So remember, I start at negative infinity and I end at a positive infinity. Okay, we also have domain and range, which isn't listed on your paper, but we're going to just do that really fast. Domain. As I go left and right, it forever goes left, it forever goes right. Yay, all real numbers. Range, as I go up and down, this is the lowest point on my graph. Everything is existing above here, and range is in terms of y. So this time I'm going to use that y value. My graph is greater than or equal to a negative 25.82. All right, I know that was a long one. There was a lot of information. Most of it was review, and hopefully we sharpened up those calculator skills that we had, but we are finally done with this video.